Chapter 9, slides 14 to 18. Okay, this set of slides is interesting, and I created it as its own grouping. And the interesting thing about it is that we're going to get the same type of products that we just saw because we're going to be reacting an alkene as the functional group with HBr again. And you're going to go, what? Right? What do you mean? We just did that. It's an acid. But here's something different. Remember that, so this is a review right here. Review. What we just covered was something like this alkene reacting with HBr. And the major product was always going to put the carbocation at the more substituted position because it's more stable. And then you finish it out with SN1, the bromine attacks, and you get the bromine at the more substituted position. But what if that's not what I wanted? What if the minor product is what I wanted? What if I wanted that? I wanted the primary bromide, not the tertiary bromide. Maybe I want to do some SN2 chemistry next. I don't know. This is my new goal, but it's not going to be formed largely if I just use HBr. This is where a change in the reagents can actually help us. This change in reagents, however, also prompts a different mechanistic motif. Notice now that we're using peroxides and light in combination with HBr. This is going to turn the mechanism on its head. This is not going to undergo carbocation rearrangements anymore, but it's going to follow all the stability rules we know and love. So how does this work? Well, in solution, you have hydrogen peroxides, and like Br2, and there's a reason. I'm going to come back to this set of slides much later after we talk about some other reactions. But notice that we're using peroxides and light. Just like with the bromine, the peroxides, those two oxygens, are very electronegative, and they're both fighting over the shared bond between them. This is why, hydrogen peroxides in your bathroom are kept in a dark brown bottle, because you don't want light causing these to form radicals. Just a little bit of photons is enough energy for that bond to break and the oxygens to break apart and form two equivalents of OH radical. Yes, the oxygen has two other lone pairs, but you form this radical species. This is the initiation step. There's actually another initiation step. This OH radical, in the presence of HBr, because who's more reactive? The very polar HBr or the pretty non-polar alkene? That high energy radical is looking to react with something very obvious, and the most reactive species with high polarity is the HBr. So what's going to happen is the oxygen is going to want to form a bond with the hydrogen. To make that bond, it will use its radical, and the HBr will break, and the hydrogen will use one of its electrons, and you're going to form a Br radical. Now, you might be asking yourself, what the heck? Why is she going through all this work just to make a bromine radical? Couldn't I have just started with Br2 and reacted that with light like I did before to get to a bromine? If the radical bromine is all she wanted, why the heck did she go about with this hydrogen peroxides and HBr stuff? Well, there is a reason. I'm going to come back to why we didn't do this a little bit later on in this chapter. Okay, it'll make sense. But for reasons that will become clear later, we had to form our Br radical this way. Okay, now what? Well, the Br radical is highly reactive, and it's looking to react with my alkene. Okay, so here's what's going to happen. The alkene and the bromine are going to come together. The carbon of the alkene, one of the carbons of the alkene, is going to form a bond with the bromine, leaving a radical behind. Do I want to form the bromine bond here, leaving the radical behind? Or do I want to form the radical here if the bromine forms at the tertiary position? Look at these intermediates. One of them is more stable than the other. Which one do you like better from a stability standpoint? They're radicals. Radicals are just like carbocations. So if you said the tertiary is better, the tertiary radical is better than the primary radical, you would be correct. So this one is not going to be largely seen. The major product, therefore, is going to stem from this tertiary radical formation. So let me go back and show you the mechanism here. That means the bond between the carbon and the bromine is going to form right here. The radical will be used to make that bond along with one of the pi bond electrons. The remaining one goes into the adjacent carbon, giving us the tertiary radical with the bromine on the far end. To finish this out, all I need to do now is react it with whatever is left. Again, don't touch your initiation steps. These were the initiation steps above the line. I don't need to do any of those. So what's floating around in solution to keep things going is the HBr. Remember, propagation steps propagate, continue the cycle. So I'm going to form a hydrogen-carbon bond right there. That bond will be comprised of the radical plus the electron from the HBr, and the remaining electron goes into the bromine. So my final product is the anti-Markovnikov, right? Markovnikov means you put your halogen on the more substituted, but Markovnikov was seeing something in lab. He didn't understand the mechanism. He just saw a trend. The mechanism comes much later in understanding why we see the trend, and it makes sense. We want to form, according to this, we want to form the radical that's the most stable because we're making a carbon Br bond first, not a carbon hydrogen bond first. And the byproduct after this step would be another Br radical, right? The Br leaves. So that Br radical can go and interact with another alkene. Round and round it goes until you get some termination steps. So really, this is just an alkene with a Br radical reaction. The only weirdness is that you're generating the Br radical in a different way than we did before. This, if you notice, gives us what we wanted. We wanted the bromine on the less substituted carbon, and that's exactly what we got when we use these anti-Markovnikov conditions. I'm not too concerned that you're going to throw these fancy terms around properly. I'm more concerned that you recognize, it's going through a different process, so it's going to give us something different. Compare the following reactions. What do you notice? Go through each mechanism and prove it to yourself. Using a different mechanism, relying on a different reagents that use different mechanisms, allow for, again, regioselectivity differences. We can control where we want the Br simply by introducing a certain set of reagents over another. We have control in the lab. Where do you want your bromine to form? Oh, depending upon what your design is, you can control that now. I leave you with a few more examples to practice and flex, right? Predict the products for these scenarios. I will add that for this one, you should have some light. And for this one, you should have some light and some light. And lastly, some more reactions to practice.